Good afternoon, everybody. This is Drew Ellsbury with Heat Pipe Technology, welcoming you all to another in the series of A Wonderful World of Heat Pipes. A few quick notes. One, I know the duration says it's going to take an hour and 15 minutes. That's not how long it'll take. Probably won't even take an hour. But at the end, for anyone interested, PDH certificates for 1 hour will be available. Just shoot me an email. My email is going to be the last slide of this, but it's just drew@heatpipe.com. And any questions that you have throughout, go ahead and type them into the Q&A part, and when we're all done, we'll see what kind of questions we have and try to answer as many possible with the time we have. So without further ado, today we're going to specifically talk about the Florida Building Code and how heat pipes, specifically the wraparound heat pipe, can be utilized to meet Florida Building Code and how we can best fine-tune it to make it most worthwhile. And I am going to relate this to other states. I mean, even though I'm going to specifically look at Florida conditions, so to speak, it does tie into other state energy codes as well, so we'll cover those. But I'm going to start off, of course, I don't want to assume everybody here knows exactly what a heat pipe is and how it works, so I will do a quick refresher course on what a heat pipe is. And then, of course, we're going to cover the Florida Building Code and specifically the energy recovery portion of the code and how the heat pipe applies to it. And then when it comes to energy recovery, typical ERV with an enthalpy wheel is the most common solution out there. So I want to compare, if you went the heat pipe route versus the ERV route, how that would compare. And then, of course, taking it a step further, making a heat pipe controllable and just some different installation features and a couple of local case studies to wrap it all up. So to get you all started, there is your basic heat pipe. It's, in simple terms, a tube that's got refrigerant in it. And when you apply heat to one end, the refrigerant on that end picks up the heat and flashes to a vapor. And when it boils and flashes, that vapor is going to want to go to the cold area, which is at the other end of the heat pipe. So now the vapor is on the cold area, gives off the heat, and condenses back to a liquid, where now that incoming vapor pushes that liquid back to the other end, and that cycle will continue, moving heat from one end to the other. The refrigerant is constantly phase changing from a vapor to a liquid back to a vapor as long as there's a delta T. So that's really our only driving force, is requiring temperature differential from one end to the other. That creates the pressure differential inside. We don't need any pumps. We don't need any motors. Hence the beauty of the heat pipe, heat recovery without any power required. So we actually take it a step further here at HPT. We don't use that single tube type circuit on the previous screen. We use what we call a loop circuit. And it does the same thing of moving heat from one end of the circuit to the other, except now it's in more of a racetrack type loop. Picture that loop in a vertical type setting. Picture the air going in and out of your screen. And if you didn't have any air movement or it was the same temperature, you would just have some liquid refrigerant sitting at the bottom of that loop. All of a sudden you apply hot air to the right side, cold air to the left side, and the refrigerant on the bottom right is going to pick up the heat and boil. It's going to go up the loop and around, and as soon as it gets the cold air stream, give off the heat, condense back to a liquid, and keep going around, in this case, a counterclockwise loop. And then when the season changes and that hot outside air, let's say, turns into cold outside air, then it will just reverse direction all by itself. So we take these loops and basically stack a bunch of them together, so many high, so many rows deep, so long. Each one's its own individual circuit, but when you add them all up, you get a bunch of BTUs out of it. So right there, that's what we call our heat recovery module, and it's just simply moving heat from one air stream to the other, whether we're pre-cooling hot outside air by dumping that heat in the exhaust air, or preheating cold outside air by taking heat from the exhaust air and dumping it in the outside air. It's just basic heat recovery, except for, again, we're using a passive refrigerant phase change based heat pipe loop circuit. Now what we're going to talk about today is the wraparound heat pipe. It's the same concept, except now that loop circuit's in more of a 3D type scenario where you can see you got the hot air coming in from the top left, and the refrigerant in that loop is still going to pick up the heat, and it's going to boil, and it's going to go to the other end, except now that other end of that loop is not in another airstream. We've simply wrapped it around the cooling coil so that we can just redistribute that heat as reheat. So why would we do that? Well, we have to keep our spaces not only cool when it's hot outside, but we got to keep it low humidity as well, keep it somewhat dry. ASHRAE actually tells you got to keep the relative humidity below 65% all the time, which isn't too hard. I mean, most designs are probably around a 50%, maybe 55% relative humidity setting. The problem you have is maybe on a day when it's relatively cooler outside and maybe it's raining and you're bringing in a bunch of that outside air, and the thermostat is going to tell you that it feels great. Don't do anything with this. Maybe cool it down a little bit, but you're bringing in so much moisture, your humidistat's going to feel quite differently. So what do? Essentially, you overcool the air to wring out all that moisture, but then you got to heat it back up so you don't freeze everybody. It's also a pretty common strategy for part load control. Let the cooling coil handle the dew point of the air, let it handle humidity, and then based on the sensible load out in the space, reheat is added to meet that set point. Very common strategy, very useful, but also can be very expensive because as much as cooling costs, heating costs even more. And that reheat, though you got to keep the space comfortable, reheat can get quite expensive. Not to mention, codes are actually getting a lot stricter. 90.1, the latest version, actually tells you that you can't simultaneously cool and heat anyway, unless a majority of that heat is what they call site recovered. So the latest version, 2013, tells you that 90% of that reheat has to be site recovered. If you go back to older versions, most state building codes, like Florida building codes, are based on an older version than 2013. It's saying the same exact thing, except 75% of the reheat has to be site recovered. So if you had a DX system, that's not too hard to accomplish. You got hot gas reheat, that's site recovered waste heat that can be utilized to accomplish this. If you got a chill water system, it's a little harder to accomplish. And that's where the wraparound heat pipe comes in. Again, we're taking the heat out of this incoming air and just wrapping it around the cooling coil, redistributing as reheat. So we're accomplishing a couple of things here. One, we've pre-cooled the air for the cooling coil, so either we've reduced the load that the cooling coil has to see, saving you on some cooling energy, or we allow the same cooling coil to do more latent cooling and drive the dew point down a little bit further. But the important part here, because there's many things that can pre-cool the air, is that we've taken that heat and reused it as reheat. So you're saving on both sides of the cooling coil there. And even hot gas reheat is free reheat, but it's not doing any cooling for you. We're both cooling and heating that air, so you're saving both cooling and heating energy. If you put that on a site chart, you'll see that we're pre-cooling the air from essentially point A to point B. So if we had a cooling coil that had to get down to, let's say, a 50-degree dew point, you'd have to have a coil that's essentially doing as much work as A all the way down to C. Now we've done the work to go from A to B, so you only need a coil that can go from B to C, whether that's less capacity coil or just less GPM if it's chill water. Or if you had a coil that was already going down to 50-degree dew point and now we're pre-cooling the air down to point B, now that same cooling coil will be able to drive down to a lower dew point using the same amount of energy or with the same amount of capacity going through it. And then, of course, whatever heat we've extracted from point A to point B, we've just redistributed as free reheat from point C to point D. So that heat is always going to be the same BTUs. And we call this wraparound heat pipe our dehumidification heat pipe. So whenever you see the model number DHP, that's what we're talking about. It's a dehumidification heat pipe. So we use this essentially whenever reheat is required to control humidity. Now, we use it a lot. It's great for indoor air quality. I mean, obviously, the drier the air, the better. Back in the day, before many of you listeners' time, there was things called sick buildings where it wasn't being dehumidified enough, and you had mold growth and stuff like that. So indoor air quality, it's built into all designs now. It used to be a tricky subject back in the day, and you know, back when we started doing these 30 years ago, it was all about improving indoor air quality. But we're going to focus on the energy side today, and on the energy side, it's all about the reheat. So a neutral air type system where you're providing more reheat than usual, still got to dry out the air, but reheat it back up. And that's right in our wheelhouse of not only giving you free reheat, but free cooling to get it. And our neutral air system means more reheat than usual, which means even more pre-cooling than usual, which is even better savings. But any high percentage of outside air system, we see lots of dedicated outside air systems, make-up air units. Those are where heat pipes really do the trick for you. Not as many chilled beam systems down here in Florida or even in the southeast really, but when you do have some, you have less air, so it needs to be drier to do the same amount of latent cooling, and we help that coil dry out the air even more than it would all by itself, and then reheat it back up because you don't want to send 50-degree air out to the space. And even underfloor air, there's not a whole lot of those these days, but again, you don't want to send 50-something degree air out at your feet. You got to reheat it back up, and at the end of the day, it's all about the reheat is where you get the savings. But let's focus on Florida Building Code. So if you get into it, you'll find that ASHRAE has this nice climate zone map. It's broken out to, well, you got your marine climate, which is the west coast. You got your dry climate, which is basically the western half of the U.S. And then we're all in this, what we call the moist climate, or the A zone, so to speak. And then you've got different temperature ranges. Obviously, the further south you get, the hotter the climate is. So whether you're in 1, 2, 3, or 4, actually, per code, you all fall under the same requirement because we're all in the A zone, or the moist zone. And what Florida Building Code tells you is that, first of all, if you have a minimum of 30% outside air in your system, you might need to have energy recovery. And then there are supply CFM requirements. So at 30%, you can see the left column there, that if you had at least 5,500 supply CFM and at least 30% of that is outside air, then it requires you to have energy recovery. But more importantly, if you look over the way to the right, if it has 80% outside air or higher, so any 100% outside air system will require you to have energy recovery. Now, this is actually tied to 90.1, the 2010 version, which is very similar to 2013. 2013 is the same table, except the airflows are lower. So basically, as time goes on, all these energy codes are getting more and more tight. If you go back in time, the old Florida Building Code was tied to an older version of 90.1, as are many other states, 2007 or prior, and those simply told you that if you had at least 5,000 CFM supply air and at least 70% of that was outside air, then you had to have energy recovery. So that's the old Florida Building Code, minimum of 5,000 CFM and 70%. Now, if you had 1 CFM and 100% outside air or even 80% outside air, you're going to have energy recovery. What the difference between this and 90.1 is that 90.1 actually breaks these tables down into number of hours, more than or less than 8,000 hours in a year of operation. Florida Building Code said, forget that, let's just go with the full 8,000 hours plus. So basically, if you got a 100% outside air system, you have to have energy recovery. And it's not just any energy recovery, it has to be at least 50% effective. And not just any effectiveness, it has to be enthalpic effectiveness. So when we're talking enthalpy, we're talking sensible and latent heat. So what can meet this requirement? Well, the most common solution to this is your basic wheel, which can be sensible only, desiccant or latent only, or what we call an enthalpy wheel that recovers both sensible and latent heat. Now, this has no problem meeting that code requirement. You got to hit at least 50%. Most enthalpy wheels are going to be 70% or higher. They're the most effective device on the market and therefore the most commonly used. However, wheels do have some downsides. If you have a critical application where you can't cross-contaminate whatever's in the exhaust air back into the supply air, you can't use a wheel. It will always leak something. But in more basic applications, you know, they're pretty maintenance heavy. You got to keep it turning, which means there's moving parts. You got to belt a lot of times. You got to keep it clean. So most of the time, the biggest downside of the wheel, especially if you talk to a maintenance guy, is just it's a little bit more of a headache than other devices. Relatively speaking, it has the highest static pressure losses compared to other devices. It will have leaks. You have a purge device you got to consider. Not very flexible from a design standpoint. You got to bring the exhaust air duct right up to the outside air at some point so you can have these adjacent cross counterflow air streams. You got to bring power to it. It's not a passive device, so you do have to keep the wheel turning. A lot of times that requires a drive. And they don't last a long time. I mean, not all wheels are equal. Some are going to be more effective than others. Some are going to have less or more static pressure than others, and some are going to last longer than others. But in general, they don't have a very long lifespan, so they are going to have to be replaced sooner rather than later. Kind of next in line from an effectiveness standpoint would be your fixed plates. Now, they're not as effective as wheels, but they're still 60+% effective. Again, meeting code that requires you to hit 50%. It is, and there are plates out there that can recover both sensible and latent heat, so they're going to hit that enthalpy mark. They don't have any moving parts, so not as maintenance heavy, and they won't have any cross-contamination. So if you got a critical application, you can use a plate. The biggest downside to the plates is just space. They take up a lot of space. Each one of their cores aren't small, and if you have large airflows, that requires multiple cores all stacked together, and then that requires even more space, which ties into not giving you a lot of flexibility in a design. You have to make them work. Again, you have to bring the air streams together, and if those plates do get a little dirty, they're not easy to clean, especially if you have multiple of them stacked together. You got to get in there or pull them out, and that can get difficult. Now, we do have heat recovery heat pipes. We call it the HRM, or the heat recovery module. We got a lot of flexibility with these. You know, it's not a one size based on an airflow range like other devices, like the plates and the wheels. We can change fin height. We can change fin length. They're going to last considerably longer. Maintenance-wise, you just got to clean them whenever you clean the coil, no cross-contamination. We can actually separate the air streams up to 40 equivalent feet, still make them work. So a lot of pros, but from an energy code standpoint, even though we have the least static pressure associated with us compared to the other devices, we do hit 50% effectiveness but not enthalpic effectiveness. We're a sensible-only device. We can't recover latent heat. We can remove latent heat in the form of condensation in many cases, but we're not recovering it from one airstream to the other. So if we were 55% effective, which our 6-row is around, can be around 55% effective, well, that sensible side, that's going to be, or translate to being around 40% effective enthalpy-wise, and that's in heating mode. So that we're talking up north. So up north, we can actually add rows to this and meet that 50% enthalpic requirement in many cases. But down south, where there's a lot of cooling hours and there's a lot of humidity, the HRM is not going to hit the 50% enthalpic effectiveness requirement that is out there for Florida Building Code. But don't worry, that doesn't stop us, because fortunately, as with many requirements, there are exceptions. Now I'm going to read off every single, I'm kidding, I'm going to skip right down to number 7. There are actually several exceptions there that you can go in your own time and check them out. I'm not going to tell you that we're the only one, but if you go down to number 7, you'll see this as an exception to that energy code requirement. If you have a system requiring dehumidification that employs energy recovery in series with the cooling coil. Now, I guess the question then is, what the heck does that mean? Well, that is a very ASHRAE way of saying a wraparound heat pipe, because if you think of a wraparound heat pipe, it is recovering energy upstream of the cooling coil and redistributing that energy downstream of the cooling coil. So all this energy recovery is in series with the cooling coil. So essentially, and the first part of it is that it's systems requiring dehumidification. Well, if this is a 100% outside air unit in the Florida or even a southeast climate, I'm sure you're worried about dehumidification, and it is energy recovery in series with the cooling coil. So essentially, if you use a wraparound heat pipe in your outside air unit, you have met code. You do not have to do anything else. And there are some that have questioned whether or not a heat pipe is the same thing as energy recovery in series. Well, don't worry. We actually reached out to the Florida Building Commission and asked point blank, does this apply? Yes, it is acceptable. It is a dehumidification device that employs energy recovery in series with the cooling coil. So we thank Mr. Richard Browdy. So anyone who has any doubts, those doubts are now put aside. Now, some of you, I know we had people sign up from other states, and you're probably wondering, why do I care about the Florida Building Code? Well, just know that at the end of the day, it all ties back in to ASHRAE Standard 90.1. Florida Building Code is almost exactly what 90.1 2010 is saying. If we go to Georgia, for example, the Department of Community Affairs tells you that energy code is based on the IECC, or the International Energy Conservation Code, the 2009 version, which itself ties right back into ASHRAE Standard 90.1. The 2007 version. So in Georgia, in 2007, 90.1 told you that minimum supply air of 5,000 CFM and a minimum percentage of 70% outside air requires energy recovery, and you have the same exception for a wraparound heat pipe. Alabama, the Alabama Building Commission just tells you straight up, just look at Standard 90.1 2007, which again, same thing I just said for Georgia. And each state's a little bit different. Tennessee, for example, doesn't have a state mandate, but each city tells you that IECC 2012, which is based on the 90.1 2010, again, it all ties back to 90.1. And whether it's 01, 04, 07, 10, 13, they're all telling you you have to have energy recovery, and they all give you the same exception that of the energy recovery in series with a cooling coil. So whatever code you're looking at is all based on 90.1, and it's all allowing you to use a wraparound heat pipe as an exception to doing anything else for energy recovery, excuse me. So now what I wanted to do, because obviously we're not the only option, I mean the other option, that the most effective option we talked about is the enthalpy wheel. So now I wanted to actually take a scenario. I picked Tampa, Florida because I'm here in Tampa doing this, so I figured it'd be nice and easy. Basic 10,000 CFM selection, basically just a single path air handler with a wraparound heat pipe compared to an ERV that has both supply and exhaust coming by with an enthalpy wheel. We're going to say that there's 52-degree air coming off the cooling coil. Average rates for the state of Florida, about 10 cents a kilowatt hour for electricity, about $1.50 a therm for hot water. And in this case, we're going to say that you want to actually provide 65-degree air. So we're going to want to reheat the air from 52 to 65. So very common dedicated outside air type system in the state of Florida. So on a design day, and design day here in Tampa is about 95-degree dry bulb, 78 wet bulb. Again, enthalpy wheel is about 70+% effective. So I got a selection for an enthalpy wheel. It's the most, full disclosure, it's the most commonly sold wheel in the market, which is an air exchange wheel. In these conditions, it's going to be about 71% effective enthalpic-wise. It's not going to have any reheat. I'm comparing chill water systems here. If you did have a DX system, you could get hot gas reheat, so that's a whole other animal. So in a chill water system with an enthalpy wheel, it's going to be very effective, but you're going to have to add reheat to the system. And like I mentioned before, it does have higher static pressure than normal, than other devices. And again, some wheels are more effective, less effective, higher static, lower static. In this case, they're adding a little over an inch of static to each airstream. So that static and the associated fan power plus the motor to keep it turning translates to needing about 4.4 kilowatts of power to keep that wheel turning at all times. Now, if we put that on a site chart, up top you've got what that wheel is going to actually do on the design summer day of 95-78. You can see it's not only cooling the air, but it's dehumidifying it. And then what it's also doing, it may not be doing any reheat, but when it's cold outside, the wheel is going to give you some preheat. So that bottom left is showing you that it's not only going to reheat the air, preheat the air, but it's also going to humidify it before getting to the heating coil. Now, when you plug in Tampa weather bins and those rates that we talked about, you'll see that wheel at 71% effective is going to offer you about $9,500 in annual savings on the cooling side. It's going to offer you about $3,600 in preheating savings when it's cold outside. And to keep that wheel turning is going to be about $3,900 on your electric bill. So you'll get a net annual savings of about $9,200 for that wheel here in Tampa. Now let's compare it to a two-row wraparound heat pipe or our DHP model. Now I'm saying two-row because we wanted to reheat up to 65 degrees. So on a 95-degree day where you got 52 degrees coming off the coil, 2 rows is going to be about 30% effective and give you about 13 degrees of the reheat that you're looking for. A lot less static pressure, not even 0.4 of an inch. So, and again, it's a passive device. You don't have a motor like the wheel does. A lot less static, a lot less fan power. So we're talking less than 1 kilowatt of power added to the system for this wraparound heat pipe. Now you put it on a site chart. It's not as impressive. It's not doing anything for humidity. It leaves that to the cooling coil. It is pre-cooling the air. And then, of course, the same BTUs we took out upstream, we're just redistributing downstream. So that's, unlike the wheel that showed you on a design day, pre-cooling and preheating, the heat pipe savings are in the pre-cooling and reheating. And then when you look at these savings, I mean, obviously the heat pipe was less than half as effective as the wheel, so it's going to give you less than half as much cooling savings. But check out the heating savings. It's actually giving you more savings on the reheat side than the wheel does on the preheat side. And that is because, not surprisingly, in Tampa, Florida, there are a lot more cooling hours where reheat is required than there are heating hours where preheat is required. On top of that, it took very little power to overcome the static of the wraparound heat pipes. We're talking $600 of annual energy bill to fan energy. And the annual savings, when you add all that up and subtract the electrical penalty, we're talking $12,550. So essentially, in this scenario where 65 degrees is desired, the heat pipe, the two-row, is going to save you 36% more money than the ERV would. And that's just a two-row. If you wanted more neutral air conditions, like many applications, especially dedicated outside air units, like a makeup air unit where something else out there is handling the sensible load in different zones, if you're reheating up to 72-degree air, like a four-row would do, four-row is going to be about 50% more effective. It's going to add almost twice as much static, so it's going to require about twice as much power to operate. But as you can see, it's actually giving you about over $19,000 worth of savings compared to the $12,000 for the two rows. So you're actually saving over twice as much as what the wheel is going to save you in a given year. But that's a four-row. So as you can see, like I said, neutral air is almost a no-brainer. This chart really shows that. If a four-row is going to provide neutral air, then the savings make perfect sense. But even a two-row that's just providing 65-degree air is going to save you about 36% more money year over year than just that basic entropy wheel ERV would. But that's Tampa. There are obviously other states in Florida. So what happens in Orlando? Orlando's a little bit further north, so less cooling hours, but barely. So you can see that relatively speaking, it's giving you about the same savings, still about quite a bit more than the enthalpy wheel, especially with a four-row. Now, if we're talking Miami, it truly is a no-brainer. In Miami, even the two-row is saving you about 60% more energy than the wheel would, and about 2.5 times more dollars than with the four-row with an enthalpy wheel. So you can see right here that even though the ERV is more effective, it's in the state of Florida, it's proving to be, again, based on how much reheat you want, may not save you as much money as what the wraparound heat pipe can do, which will also, as I said earlier, meet code. Now, if we start creeping up towards Jacksonville, again, now we're getting a little bit further north. Not as much cooling hours, a little more heating hours. The wheel starts to do a little better relative to the heat pipe. The heat pipe is still saving you more money, especially with the four-row, but the two-row, it's just a little bit more savings there. Now, again, in Georgia, it's a different code requirement based on those 90.1/2007, so if it has to be a minimum supply of 5,000 CFM and 70% outside air. If you had an ERV in Georgia, the same wheel is going to save you about $11,000 a year, where the two-row is only going to save you a little less than $8,000 a year. So you can already see that as you're getting outside of Florida, the savings for that two-row aren't as sweet-looking. But the four-row, as you can see, is still going to save you more. So again, if you got neutral air, it's all about the reheat when it comes to the wraparound heat pipe. Now, one thing you might be noticing when you look at this chart is that the cooling savings from the four-row is actually higher than those from the wheel. And I've had some questions on that. The wheel's 71% effective. That four-row heat pipe's 46% effective. How on earth is the heat pipe saving you more on the cooling side? Well, that's because the wheel is only pre-cooling the air when the outside air is warmer than the exhaust. So a typical exhaust air is going to be at 75 degrees in cooling mode. So the wheel is only going to be working for you when the outside air is warmer than 75 degrees. The heat pipe, on the other hand, is always going to be cooling and heating whenever the incoming air is warmer than whatever's coming off the cooling coil. Well, in this case, that's 52 degrees. So anytime that outside air is between 52 and 75 degrees, the heat pipe is still giving you cooling savings while the wheel is not doing. It's essentially in economizer mode. So that's why you still get, even though it's not as effective, there's more hours where it's helping you out. But that's just energy savings. Let's look at first cost. Enthalpy wheel, I was told that an ERV was going to be about $1.50 a CFM, so at 10,000 CFM, I'd budget that at about $15,000. And maintenance-wise, relatively speaking, it's a lot more intensive than a heat pipe. Well, a two-row heat pipe, I'd budget that at about $1 CFM, so only $10,000 for that heat pipe. Nice, easy maintenance, just another coil to clean at the end of the day. In the full row, I'd budget that back up at $1.50. So if the full row is going to cost you the same from a first cost standpoint as the wheel, from a maintenance standpoint, it's obviously going to cost a lot less and take a lot less time. It's going to last a lot longer. Again, that wheel, depending on the wheel, you're going to be replacing it every 3, 5, 7 years or so, depending on the wheel and how well it's being maintained. Heat pipe, like the coil, is going to last, 20 plus years as long as you're keeping it clean. You don't need any power for the heat pipe. It's a passive device. And again, you don't have to even worry about running the exhaust air duct up to it. Just let the exhaust do its own thing. If you have multiple exhausts, doesn't matter with the heat pipe, just send them away. With the wheel, you got to pull all those exhausts together, bring it over to the unit. There's a lot more to it, and I'm only talking energy cost and first cost here, but if the energy cost is actually in the favor of the heat pipe, the first cost is maybe a wash or in the heat pipe's favor, and then all these other things are taken into account, and it meets Florida building code. So know that, each project's a little different. All these, we're assuming 65-degree air is desired. So if you ever have any jobs where you don't need 65, you need 60, or you have different leaving air temperatures coming off the coil, feel free to let us know or let your local sales rep know if you want to get a true comparison. We'd be happy to put those together for you. Now I'm going to take it a step further and talk about controllable heat pipes. Because if there's a downside to the wraparound heat pipe, it's that you may not want all the reheat that's being recovered. It's a passive device, so it's all based on the delta T. So in this case, the hotter the air coming in, the bigger the delta T, the more heat it's going to recover, and therefore the more reheat it's going to provide. But the hottest day of the year is maybe not when you want the most reheat. So we can actually put some solenoid valves on our circuits and allow them to be staged off and on as needed based on how much reheat you want or what the temperature set point is in the space. And if it starts recovering too much heat, well, hey, BAS will tell the heat pipe, hey, let's shut off the first stage of circuits. And after a given amount of time, if it's still too hot, well, hey, let's shut off the next stage of circuits. It's a pretty simple sequence of operation. It's essentially the opposite of staged electric reheat, except it's not when it's getting colder, turn on a stage of heat. It's, hey, it's getting hotter. Okay, let's turn off a stage of heat pipes. Now, we generally stage those in 3 or 4 stages. Basic solenoid valves, 24 volts. We got to go up to 120. If you got a large count, I think it's 25 valves or higher. It'll force you to go to 120. Just from a size standpoint. If you have a really big unit that requires a lot of circuits and therefore a lot of valves, it may not make sense to have dozens of solenoid valves in there. So we can actually we have a split passive heat recovery heat pipe that will overcome up to 40 equivalent feet between the air streams. We can take that same device and wrap it around the cooling coil. And now instead of dozens of solenoid valves, we can have just a handful of modulating valves. Just be careful. One, it's not as effective. We're combining multiple circuits within the coil to just a few headers getting across from one area, the pre-cooling side to the reheat side, so you lose some efficiency or some effectiveness there. It's going to cost more. That certainly costs a lot more to put those pipes together and charge it than it does the basic DHP. But it also, because we have vertical tubes running between those headers, we have horizontal fins. When it comes to energy recovery, that's not a big deal. But when it comes to dehumidification, if you have low air velocity going across horizontal fins and you have condensation built up on it, it may have trouble pushing that condensation off into the drain pan, and you have basically blocked coil of water and some issues. So if you ever had a scenario where you wanted to go to what we call the DHPV, because it has those vertical tubes, instead of just the basic solenoid, what we call DHPC for controllable DHP, if you ever are interested in going that route, we'll certainly work with you and make sure that it's going to make sense for you. But generally, it's only going to make sense in larger air streams, which is when you would have a high valve count anyway. But why are we making them controllable? Why on earth do we care? Well, again, from a controllability standpoint, that's got its own value of being able to control that reheat. If you've got a neutral air type job where you don't really, I don't want to say you don't care about the temperature that's leaving, but the more reheat is not really going to hurt the system. Other devices are out there handling the sensible load. There's certainly not much of a point to put solenoid valves on it. But if you have a system where that reheat is going to want to be controlled, like we do a lot of OR type jobs where you not only want lower dew point air with reheat, but that temperature needs to be pretty stable. It's a good reason to use some solenoid valves. But from an energy saving standpoint, a great reason to do it is to optimize the heat pipe and truly size it for part load instead of full load. So what am I saying? Well, let's use that example here in Tampa, Florida again, 10,000 CFM, 52 off the coil, reheating up to 65. And again, on the hottest day of the year, that two-row DHP is going to reheat the air 13 degrees. So you're hitting your 65-degree mark. You're adding very little static, about $1 a CFM. In Tampa, Florida, based on those rates, is going to be over $12,000 a year in savings, less than 1 year payback. That looks like a no-brainer to me. If I had $12,550, I'd buy it. But we can do better, because if there's a problem with that, it's that, yes, you're getting your 65 degrees, but you're only getting that on the 95-degree day. And 95-degree days rarely happen. So anytime it's cooler than that, which is almost all the time, you are having to add some supplemental reheat if you want 65-degree air. Well, that's where the control valves come in, because now what we can do is oversize the heat pipe. Where on a 4-row heat pipe that's fully controllable, it might reheat all the way up to 69 degrees, but that's okay. You've got valves on it. You shut off a stage or two of circuits to get down to 65. But what you've done is now you've sized it to get 65-degree air on an 85-degree day. So now whenever it's cooling down from 95 to 85 degrees, that's a lot more hours where you're getting max free reheat of up to 65 degrees. And even on the hours cooler than that, that's a lot less supplemental reheat that's needed all the rest of the time that it's in cooling mode. Yes, you have twice as many rows. Yes, you have valves on them. So yes, it's going to cost more. So I'd budget that about twice as much as a 2-row non-controllable. And it does require about twice as much fan energy to overcome that twice as much static for twice as many rows. But we're still, because we've added more rows to get more free reheat and therefore more free cooling, now our annual savings is, we're talking over $15,000 versus $12,000. Even though it costs more, it's still less than 1.5 years of payback. But now once it's paid back, that's 25% more savings year over year, because you sized that heat pipe for part load instead of full load. And now I'm going to take it a step further. Let's say you do need, in this situation, at some point in the year, maybe on that 95-degree day, you actually want 52-degree air going straight out to the space. If you did that, you would have to make it fully controllable because you got to be able to completely turn off the heat pipe or close off all those circuits. But if you're going to always want some reheat, then why would you put valves on every single circuit? So what we can do is what we call a partially controllable. Or in this case, if we had 4 rows, we'd make 2 rows fully controllable and 2 rows non-controllable. So now half the circuits have valves on them. And the valves actually add friction to the refrigerant, which takes away from the performance. So the less valves you have, the better effectiveness you get. So you can see you're actually getting more reheat because there's fewer valves. Still the same static pressure hit, but because there's less valves, it costs less. You're paying for half as many valves. So it's going to cost less, it's going to save more, you're back to a 1-year payback, and now you're saving 40% more year over year. So this is just a good reminder that use the valves not just for the inherent value of having controllability, but it allows you to more properly size the heat pipe. Again, if you want to work with us or work with your local sales rep to figure out what's the best bang for your buck, we'll be happy to do that. All of this stuff is done in our Select Plus software using our bin analysis. You can try all this stuff yourself or let us run it for you. Now, a little quick spiel on our company, Heat Pipe Technology. We were founded back in 1983. We're actually the money came from NASA and a bunch of private investors, including the founder of Gatorade. So that's actually how we started 30-something years ago, and we invented the wraparound heat pipe. So if you go look up a list of NASA-influenced innovations, the wraparound heat pipe is certainly one of them. We were acquired by a company called MyTech, which is a Berkshire Hathaway company, back in 2009. So yes, we are the offspring of NASA and Gatorade, and we have hence been adopted by Mr. Warren Buffett. So you're a very rare family tree. And we moved to Tampa about 4 years ago, Maz? Mm-hmm. About 4 years ago. So if you ever need to come over to Tampa, feel free to come by and check us out. We'd love to host you. We make these wraparound heat pipes fully assembled, what we call our U-frame, because if you look down on it, it looks like a U, and we'll ship that to the air handler manufacturers and let them install it themselves, or they can ship us their shipping splits with a coil in them, and we'll install the heat pipes inside the air handler. Now it's not fully assembled. We actually install the pre-cool and the reheat separately and then circuit up in between them, charge each of those circuits, charge as many at a time that we can. You can see on the picture on the top right, there's some sheet metal inside the crossover tubes. That's to prevent any air from bypassing around the cooling coil. We do all this in-house and then ship it on out to the job site. Or we'll even go out to the job site itself, whether it's a unit that's not dehumidifying enough or they're spending a lot of money on reheat and don't want to, or let's say it's a new installation but all shipping splits must fit through a tight space, and a full wraparound heat pipe's not gonna make that shipping split small enough. We can put the pre-cool in one split, the reheat in another, come out to the job site once it's all the units assembled and pipe everything together and charge it out in the field, whatever's needed. We don't take up that much space. I mean, you can see that the pre-cool and the reheat modules only take up about 3 to 6 inches. It's that F dimension that you really need to worry about. We don't like to penetrate the skin of any air handler if we can avoid it. So we need about a couple of inches to run our connecting tubes outside of the U-bends of the cooling coil, but inside the air handler skin. This is something we work with all the manufacturers on before it gets here or before we ship it to them. So any consulting engineers out there, don't worry about it. You don't have to concern yourself with this. We'll take care of it on our end. If we had control valves on it, those valves need more space, so now instead of a couple of inches, we need about 5 inches. But again, nothing for you to worry about. We'll take care of that ourselves. Finally, we see this quite a bit. The wraparound heat pipe is excellent for dehumidification, but when it's cold outside, again, it's not doing anything for you. So a lot of times we'll see something upstream doing some sensible heat recovery. I'm of course biased here, so I'm going to show our HRM heat recovery heat pipe, but we see a lot of sensible wheels as well. Now it's going to give you year-round savings, really enhance your product. And back to the 50% requirement, the wheel obviously is going to hit 50%. The heat pipe may not, but from a code standpoint, now you have the wraparound heat pipe in there that's going to meet code. So now if it is a critical type application where you can't allow cross-contamination, you can put the heat pipe in there. It may not hit 50%, but that's fine. The wraparound heat pipe is gonna meet code for you, and now you've got year-round recovery and really enhanced savings. And now in cooling mode, you got 2 layers of pre-cooling to really drive that dew point down even further. A lot of cool case studies. I'm just picking the ones that are 1, local, and 2, that we actually have written case studies on. The Grand Hyatt here in Tampa replaced or actually retrofitted 3 air handlers a few years back. They were using a lot of electric reheat, and now we save them about $37,000 a year, according to them. To step that up quite a bit, we actually retrofitted 16 air handlers at the Omni Resort at Champions Gate in Orlando. 240,000 CFM worth of air handlers, over $400,000 of annual savings. If you need to talk to an owner that will speak highly of a heat pipe site retrofit, this is the place to go. This guy's obviously a huge fan at almost $500,000 in annual savings. Again, I mentioned ORs as being a good application for a controllable wraparound here in Tampa at St. Joseph's Hospital. We got some OR units. The wraparound not only helps depress that dew point, but you want to reheat the air. You can't send 49-degree air out to a space. Some doctors may like that, but not all of them. So you get the free reheat, you get the dew point help, plus you got the control valves to stabilize that supply temp. And finally, if you want to go see the lightning play, because they're coming up, or more importantly, you want to feel how comfortable the air is in that facility. They actually replaced over 500,000 CFM worth of air handlers several years back because they had horrible ice quality. Now they have air handlers with dual 10-row cooling coils and wraparound heat pipes wrapping around both of them to not only help drive that dew point down, but you certainly can't send 40-degree air out to a big arena full of people. So we reheat that air back up. It's nice and dry. It's nice and comfortable. And according to their facility guy, it saves about $50,000 per month in just the heat pipes, which is really cool. So just to wrap it up, again, this is all about meeting energy code. I made it about the Florida building code, but it's all based on 90.1. So whatever state you're in, just backtrack. A lot of times it's IECC, but it all goes back to 90.1. Each year's version is different, so just understand what your code is and understand that no matter which 90.1 version it is, the wraparound heat pipe is an exception to that energy recovery requirement. It's a quick return on investment. I mean, obviously it depends on where you are, what the application is, and what your utility rates are, but generally the more reheat you need, the more savings you're going to get from the heat pipe, and the quicker the return. Even compared to ERVs, especially down here in Florida, not only is it a lot less hassle from a maintenance standpoint or having to bring duct over to the unit, period, but depending on the application, you actually have more energy savings as well as first cost savings. And make it controllable. Again, it's not just about controlling temperature, it's about properly sizing the heat pipe to really optimize your savings. And we get a lot of flexibility. We'll install them at the job site, we'll install them at our place, or we'll send them to the air handler manufacturers. We'll do whatever it takes. Chill water or DX systems, doesn't matter. As long as the coil is cooling, it'll work. And we don't take up that much room, as you can see, but again, you don't have to worry about that. We'll take care of that on our end. Finally, if you want to actually run these numbers yourself and not take my word for it, go into Select Plus at heatpipe.com. That is our design software, one of our many presents from Warren Buffett. And go in there. You can select DHPs, you can select HRMs, you can pick what city you're in, you plug in utility rates, how efficient the chiller is, how efficient the whole system is, and it'll tell you how much pre-cooling savings you're getting based on the chiller, how much reheat savings you're getting based on whether it's hot water or gas or electric heat. And it'll even back out the fan penalty and tell you what you're going to save year over year. So feel free to go do this stuff yourself or call your local HPT rep. They're all awesome. I'm vouching for them right now. And some of them are listening and nodding their head in agreement, I'm sure. Or give us a call. You can call me, 906-3177, or just email me again. Again, it's simple. It's drew@heatpipe.com. For any of you that want PDH certificates, write that email down and shoot me an email, and I'll get them to you as quickly as possible. And with that said, I thank you all for listening. And now I'm going to turn it towards John, who's handing me a list of questions. Let's see. Okay. Typically, how much static pressure will a heat pipe add to an air handler? Well, that is driven by, one, how many rows the heat pipe is, and two, what kind of face velocity you have going through the heat pipe. From the examples you saw, that the 2-row at about 500 feet per minute, I think it was like 450 feet per minute for that one, was just under about 0.4 of an inch, so that's 0.2 of an inch for each, the pre-cool and the reheat. The 4-row went up to about 0.7 of an inch or so. So depends on the number of rows. 2 rows is pretty common, less than half an inch, and then probably less than 0.8 of an inch for a 4-row. Let's see. Any program on converting to, or any progress converting to a microchannel coil? I can tell you that no, we're not looking at that. We do take a look at our fins quite a bit to see if we can improve stuff there, but we haven't gone to a microchannel route. That involves a whole new redesign, and we're not there yet. But that is a good question. I used to be a chiller guy, and I know all those condenser coils have gone the microchannel route. But no, we have not looked at that yet. And finally, where did I get that first cost pricing from? So again, obviously I got the heat pipe budgeting myself. I'd budget any 2-row at about $1 a CFM, 4-row at about $1.50. The ERV pricing, well, again, I mentioned that it was an air exchange wheel. Our local rep is also the Greenheck rep, and they said that at that airflow, or just budgeted about $1.50 a CFM. So that's right. I didn't make it up, I promise. Any other questions, John? All right. Well, hey, everyone, I thank you all. We're just under an hour, so I'm not going to give you a 59-minute PDH certificate. I'll bump it up to an hour. And again, I thank you all for joining, and we'll see you next time for the wonderful world of heat pipes. Thanks.